I want you to picture something for a second. Just go back in time in your mind. You are sitting at a small desk.
Oh no, I feel like I know exactly where this is going.
Yeah, you probably do. The fluorescent lights of your elementary school classroom are, buzzing overhead.
The dreaded math block.
Exactly. And your teacher is standing at the front of the room with a giant stack of index cards.
The flashcards. The absolute worst.
Right, the flashcards. It's time for the multiplication tables, and it's a total race against the clock. The teacher's just shouting like 5 times 8, 7 times 6, 9 times 4.
And if you're anything like me, your mind just goes completely blank.
Completely blank. For most of us, that memory is tied to a very specific kind of anxiety because, well, we were always told that these numbers were just arbitrary facts.
Right, like there was no underlying logic to memorize, no pattern to grasp. You just had to know it.
You either knew it instantly or you failed. It was just this binary thing.
It was an exercise in pure brute force memory. And it's fascinating how universal that experience of anxiety actually is.
Oh, absolutely.
We tend to treat multiplication as this rigid, just unyielding mountain of isolated data points that every child just has to conquer through sheer repetition.
Exactly. But what if all of that rote memorization, like the flashcards, the endless skip counting, the tears at the kitchen table, what if all that was completely unnecessary?
That is a massive what if.
It is. And that's exactly why we're here today. On this deep dive, we are exploring a really fascinating text by Fred Duckworth, and Duckworth makes a bold claim here.
Very bold.
He argues that multiplication facts are not random at all. They are entirely predictable.
Which totally flies in the face of how most of us learned it.
Right. So our mission today is to basically crack this code. We're going to explore what Duckworth calls the secret patterns of multiplication.
And to be clear, these aren't just neat little parlor tricks.
No, not at all.
They're systematic ways of reasoning that allow anyone to automatically reveal these products in one fell swoop. We're basically looking for the hidden logic of mathematics that, frankly, most of us were never taught.
I love that. And framing it as logic rather than tricks is really important here, right?
It's crucial because traditional math education, it relies heavily on visual models like drawing arrays or area models or using those little wooden blocks to show a student what multiplication physically is.
Right. To build that conceptual understanding early on.
Exactly. But eventually those tools are taken away and the student is still just left to memorize the final product.
You still have to memorize that 6 times 7 is 42.
Right. But Duckworth's approach is fundamentally different. He's arguing for discovering meaningful numerical connections.
So he wants to replace that brute force memory with systematic reasoning.
Yes. It's a massive psychological shift from just staring at a flashcard and hoping a number magically pops into your head, to actually understanding the internal mechanics of the numbers themselves.
Okay, I am so on board with the promise of this. But before we get into the specific numbers, and I know we have some genuinely wild methods coming up for the 5s and 6s, we have to start with the foundation.
We definitely do.
The source text begins by establishing a universal logic that governs all 2-digit products.
Right, because if you don't understand the boundaries of the numbers, you're still just blindly guessing.
So what's the core rule here?
Well, Duckworth points out something so simple, yet it's entirely overlooked by most learners. Let's look at any multiplication fact where you are multiplying 2 single digits.
Okay.
The foundational rule is this. The first half of the product, meaning the digit in the tens place, is always going to be less than the smaller of the 2 factors you are multiplying.
Okay, let's unpack this because I want to make sure I'm really getting the underlying mechanism here. How does that actually work in practice?
Let's take 5 times 8.
Okay, 5 times 8. The smaller factor is 5.
Right, because all single digits are less than 10. 5 times 8 must logically be less than 5 times 10.
Oh, okay. And we all know 5 times 10 is 50.
Exactly. So the product of 5 times 8 has to be less than 50. That means the digit in the product's tens place must be less than 5.
I see. It's a mathematical certainty based on our base 10 system.
Yes. Similarly, 3 times 6 must be less than 30, so the tens digit is 2 or less. 7 times 9 must be less than 70, so the tens digit is 6 or less.
So the tens digit is always capped by the smaller factor.
Always.
I follow the logic, but I have to push back here for a second.
Sure, go for it.
Just knowing that 5 times 8 is less than 50 leaves a massive margin for error.
It does.
The answer could be 48, but it could also be 12. If I'm a learner trying to master this, how does just knowing the ceiling actually help me? It doesn't give me the exact answer.
You're entirely right, and just knowing the ceiling isn't enough to achieve mastery.
Right.
That's where Duckworth introduces the deeper rule that tightens that boundary significantly. It's not just that the tens digit is vaguely less than the smaller factor.
Okay, what is it then?
The rule is that the digit in the tens place of any two-digit product will almost always be exactly one less or exactly two less than the smaller factor.
Wait, really? It's always exactly one or two less?
Almost always, yes. Think about what that does for your brain.
It narrows the first half of your answer down from, like, this infinite sea of possibilities to just two specific options.
Exactly. Let's go back to 6 times 8.
Okay. The smaller factor is 6.
Right. 1 less is 5, 2 less is 4. So mathematically, the answer absolutely has to be in the 50s or the 40s.
It must be 50-something or 40-something?
Yes. And as we know, 6 times 8 is 48.
Let me try 1 just to test it.
Yeah.
7 times 5.
Go for it.
The smaller factor is 5. 1 less is 4, 2 less is 3. So the product must be in the 40s or the 30s.
And it is.
It's 35. Okay, but wait, you said almost always. I'm looking at the text here, and there are a handful of exceptions where the tens digit is not 1 or 2 less.
Yes, there are.
It looks like there are 5 specific exceptions where the tens digit drops further. It's exactly 3 less than the smaller factor.
Good catch. That's the middle digits exception. But even the exceptions follow a strict, predictable logic.
Oh, really?
Yeah, they are very easy to spot because they only occur when one of the 5 middle digits is being multiplied by itself.
By middle digits, you mean 3, 4, 5, 6, and 7.
Precisely. We're talking about squaring those numbers. 7 times 7, 6 times 6, 5 times 5, 4 times 4, and 3 times 3.
Let's look at the math there. 7 times 7 is 49. 4 is exactly 3 less than 7.
Yep. 6 times 6 is 36. 3 is exactly 3 less than 6.
5 times 5 is 25. 2 is 3 less than 5. 4 times 4 is 16. 1 is 3 less than 4.
You've got the pattern.
And if we follow that exact same logic all the way down to 3 times 3, which is 9.
Think about what happens there.
If you take 3 less than 3, you get 0. Which perfectly explains why there is a 0 in the tens place. It makes it a single-digit product.
Exactly. The mechanism doesn't break. It holds up perfectly, even down to the single digits.
That is so cool.
What's fascinating here isn't just the math itself, but the cognitive shift it creates for the learner.
How so?
Recognizing these boundaries changes their entire approach. They are no longer searching a random mental database and guessing blindly. They are making a highly educated, logical deduction based on the inherent boundaries of base 10 numbers.
It changes the game entirely. Now that we have that foundation established, let's explore how we lock in the exact answer.
Let's get into the specific tables.
And we can quickly clear the board of the universally understood rules, right? Like, anything times 0 is 0. Anything times 1 is itself.
Right, and anything times 10, you just append a 0, and anything times 11 is just the digit written twice.
Right. But the patterns Duckworth introduces for the other numbers are where you really see the gears of mathematics turning.
They really are.
If it's all right, I want to start with the 9 times table.
Let's do it. For the 9s, Duckworth uses a number line and what he calls partners. Yeah, partners are simply any two digits that add up to a sum of 10, like 7 and 3 or 6 and 4.
Okay, simple enough.
To get the product of a digit times 9, you take the numeral that comes just before your digit on the number line to find your tens place.
Okay.
Then you pair it with your digit's partner to find your ones place.
Okay, let's test this with 7 times 9.
Walk me through it.
The numeral that comes immediately before 7 on the number line is 6, so our tens place is 6.
Exactly.
And the partner to 7, the number you add to 7 to get 10, is 3. Put them together, and you get 63.
Perfect.
Let me do another one just to make sure I have it. 9 times 3. The number before 3 is 2. The partner to 3 that makes 10 is 7. 27.
It works perfectly every time.
It does, but I have to ask, why does this work?
The million-dollar question.
Right, because I don't want us to just replace flashcards with arbitrary party tricks.
Yeah.
What is the actual mathematical mechanism here?
That is the perfect question, and it all comes back to our base 10 system. Multiplying by 9 is mathematically identical to multiplying by 10, and then subtracting one group of the original number.
Okay, let me visualize that. So, with 7 times 9.
Think of it as 7 times 10, which is 70.
Right.
But you don't want 10 groups of 7, you only want 9 groups. So you subtract one group of 7 from 70.
Ah. And because you are subtracting from a multiple of 10, the tens place drops down by 1 from a 7 to a 6.
Exactly.
And because 70 is a clean multiple of 10, when you subtract 7 from it, the ones place will always be the difference between 10 and 7.
Which is 3. Hence the partner to 10.
Wow. The trick isn't magic at all. It's just a heavily streamlined version of base 10 subtraction.
Exactly. It's just doing the algebra without writing out the algebra.
That is so deeply satisfying to understand. But let's see if you can explain the logic behind the next one, because this is where things get wild.
The 5s.
Yes. Duckworth's method for the 5 times table honestly sounds bizarre at first glance. It involves decimals.
It does, which scares people initially.
Right. Introducing decimals to a kid trying to learn basic multiplication seems like it would make things harder, not easier.
It sounds counterintuitive, but it's actually incredibly fast. It's called the decimal drop method.
Okay, how does the decimal drop work?
To find the product of any digit times 5, you simply write half the value of that digit as a decimal number, and then you just drop the decimal point.
Okay, let's walk through it slowly with 7 times 5.
All right. What is half of 7?
Half of 7 is 3.5.
Now drop the decimal point.
And you have 35. Oh, wow. It really works.
Let's do an odd number that usually trips people up. 5 times 3.
Okay, half of 3 is 1.5. Drop the decimal and you have 15.
See? It's incredibly fast.
It is, but again, I'm stuck on the why. Why does injecting a decimal point and then erasing it mathematically produce the right answer?
Think about the relationship between 5 and 10. 5 is exactly half of 10.
Right.
If we use currency as an analogy, it makes perfect sense. Multiplying by 5 is the same as counting $5 bills. If you have 7 $5 bills, that is exactly half the value of having 7 $10 bills.
Okay, I'm with you. 7 $10 bills is $70.
Right. And half of $70 is $35.
Oh.
The decimal drop trick is just a mechanical shortcut for doing two things at once, dividing by 2 and multiplying by 10.
So when you take half of 7, you get 3.5.
And when you multiply 3.5 by 10, you move the decimal point one place to the right, giving you 35.
Dropping the decimal is just a faster physical way of saying multiply by 10.
Exactly.
Oh, wow. It's brilliant because it leans on the fact that multiplying and dividing by 10 in our number system is just effortless for us.
Completely effortless. Which brings us naturally to the 6s.
Right, because if I'm following the logic, if 6 is just 5 plus 1, then the pattern for the 6s shouldn't break the system, it should just add a step to the 5s. Right?
That is precisely how Duckworth handles it. The 6 times table builds directly on the 5s using the exact same decimal drop.
Okay, but with an extra step.
Just one extra final step. You add the original digit you were multiplying.
Let's visualize this for the listener. Say 9 times 6.
First, we treat it like a 5.
So half of 9 is 4.5. Drop the decimal to multiply by 10, which gives us 45.
But we don't want 5 groups of 9, we want 6 groups of 9.
So we take that 45, and we add one more group of 9. 45 plus 9 is 54.
Look at that. You just intuitively use the distributive property of multiplication without using any of the confusing jargon.
It just makes sense. Let's do 6 times 4.
All right. Half of 4 as a decimal is 2.0.
Drop the decimal point, you get 20. Add the original digit, 4 to 20, and you get 24.
It works every time.
But wait, for the even numbers in the 6 times table, like 6 times 4, Duckworth has a variation that is even cleaner.
Oh, the half and whole trick.
Yes, this was my favorite part of the text because it is so beautifully elegant.
It really is.
If you are multiplying an even digit by 6, you don't even need to think about decimals or adding extra groups. You just write half the value of the digit, followed immediately by the total value of the digit.
It is strikingly simple. Let's look at 6 times 8.
Okay, half of 8 is 4. All of 8 is 8. Put them next to each other. 4, 8, 48.
6 times 8 is 48.
Let's try 6 times 2. Half of 2 is 1. All of 2 is 2. 12.
And this works purely because taking half of an even number gives you a clean, whole integer for the tens place, with no messy decimal to carry over.
It's like finding a hidden cheat code in a video game you've been playing your whole life. You know, once you know the developer's logic, you can bypass the grind entirely.
That is the perfect analogy. And that realization that there are hidden passageways is what shifts a learner from being a passive consumer of flashcards to an active participant who actually understands how the math is constructed.
It's incredibly empowering. Now, we've done a lot of mental manipulation here.
We have.
We've thought about base 10 boundaries, decimals, and half values. But the text is about to shift from mental gymnastics to something incredibly physical.
Yes, this is where it gets really tactile.
Because for the 2 and 8 times tables, Duckworth provides physical representations using our own hands.
Grounding the abstract math in the physical world is so helpful for learners. Let's start with the 2 times table.
Okay.
If you are listening right now and you aren't driving, hold your hands up.
Okay, my hands are up.
We all know we have 5 fingers on one hand and 10 total. When we multiply a digit by 2, we were just doubling it.
Right.
Duckworth uses the natural base 5 and base 10 structure of our hands to represent this visually. The rule is, if the digit you are multiplying by 2 requires all 5 fingers on one hand, meaning the digit is 5 or greater,
Then what?
you automatically write a 1 in the tens place.
Why a 1?
Because if you have at least a full hand of 5, doubling it guarantees you hit 10, meaning you've crossed the threshold into the double digits.
Okay, that makes perfect sense. So what about the ones place?
For the ones place, you simply double whatever fingers are raised on the other hand.
Let's do an example so the listener can follow along physically. So let's do 7 times 2.
Okay, show 7 on your fingers.
To show 7, I hold up one full hand of 5 and then 2 fingers on my other hand.
Right, because you have one full hand raised, that tells you to put a 1 in your tens place.
Got it.
Look at your other hand.
I have 2 fingers raised.
Double those 2 fingers, and you get 4. So your ones place is 4.
The answer is 14.
It is incredibly intuitive.
What if the number is less than 5, say 3 times 2?
Well, you only need 3 fingers. Because there is no full hand of 5 raised, the tens place is 0.
Oh, I see.
You just double the 3 fingers you have raised, and you get 6.
It takes the abstraction of doubling and puts it literally in the learner's hands.
Exactly.
But if the 2s are straightforward, the 8s are where the text introduces a little poetry.
Oh, the rhyme.
Yeah, because the 8 times table is historically one of the hardest for learners. The numbers get large fast, and they don't have the clean rhythm of a 5 or 10.
They really are the stumbling block for a lot of kids.
So Duckworth offers an actual physical rhyme to solve any 8 times problem.
And it goes, subtract the hands who came to play, and double the fingers who sleep all day.
Okay, this one requires a bit of careful explanation, but once the logic clicks, it is a brilliant algorithm.
Let's break down the first line. Subtract the hands who came to play.
What does that mean?
This refers to how many hands you physically need to show a number. To show the digits 2, 3, 4, or 5, you only need one hand.
Right.
But to show 6, 7, 8, or 9, you need 2 hands.
Because you've crossed that 5-finger threshold.
Exactly. So to find the tens place of your answer,
Yeah.
you take the digit you're multiplying by 8, and you subtract the number of hands it takes to represent it.
Okay, so if we are doing 8 times 6,
6 requires 2 hands to play. You subtract those 2 hands from the original digit, 6.
6 minus 2 is 4. So the tens place is 4. The answer is in the 40s.
Perfect.
Okay, I follow the first part. But I have to admit, double the fingers who sleep all day sounds like a confusing riddle.
It does sound a bit cryptic.
What are sleeping fingers?
Yeah.
And more importantly, why does doubling them give us the ones placed for the 8 times table? Isn't this getting too complicated to be a shortcut?
I promise it's not. Sleeping fingers are simply the fingers that are held down, tucked into your palm, when you're representing the number on your hands.
Okay.
Let's walk through 4 times 8 to see it in action, and then we'll explain the math.
Okay, 4 times 8.
First line. Subtract the hands who came to play. To show 4 on your hands, you only need one hand.
So subtract 1 from 4 and you get 3. My tens place is 3.
Got it. Now the second line, double the fingers who sleep all day. Hold up 4 fingers on your hand.
Okay, 4 fingers are up.
How many fingers on that hand are sleeping or held down?
Just 1. My thumb is tucked in. 1 sleeping finger.
Double that 1 sleeping finger.
That's 2.
Your ones place is 2. Put it together with the 3 in the tens place.
The answer is 32.
See? 4 times 8 is 32.
Let's try it with 8 times 6, since we already know the tens place is 4.
Right. 6 minus 2 hands is 4. Now hold up 6 fingers.
Okay. 1 full hand and 1 finger on the second hand.
How many fingers are sleeping on that second hand?
4 fingers are tucked down.
Double those 4 sleeping fingers.
8. So the answer is 48. Okay, the trick absolutely works, but I need you to explain the underlying logic.
I knew you would ask that.
Why does counting tucked away fingers and doubling them give us the 8s?
It comes right back to our base 10 system and the inverse relationship between numbers.
Okay, how so?
Remember how multiplying by 9 is just multiplying by 10 and subtracting one group?
Yeah, that made sense.
Well, multiplying by 8 is multiplying by 10 and subtracting 2 groups.
Oh.
Yes. When you count the sleeping fingers on a hand, you are literally finding the difference between your digit and the base 5 or base 10 threshold. By doubling those sleeping fingers, you are calculating exactly how much to subtract from the 10 ceiling to get your precise one's place.
The rhyme isn't magic at all.
Not at all.
Yeah.
It's a physical representation of algebraic subtraction.
That is mind-blowing. By translating the abstract math into playing hands and sleeping fingers, the learner isn't just reciting a hollow fact.
Exactly.
They're physically constructing the answer based on predictable structural rules of mathematics.
And we should note that while we have covered a vast majority of the multiplication tables today, there are a few we didn't explicitly break down verbally.
Right, the 3s, 4s, and 7s.
Yes. Duckworth mentions in the text that those tables involve visual matrices, irregular grids, and jagged arrays.
Which are probably hard to explain on an audio deep
It's
dive.
very hard.
Yeah.
He notes that these require visual renderings that he includes in his accompanying PDF documents.
Yeah.
Because they rely on spatial logic rather than purely numerical shortcuts.
But the core philosophy remains exactly the same, right?
Absolutely. There is always a system to be found, even in the tables we didn't touch on today.
So if we zoom out, what does this all mean for you, the listener?
Well, the impact of these techniques is that they completely flip the script on how we absorb information.
Instead of sitting at that desk, sweating over a ticking clock and panicking because your brain just went blank, you are given a toolkit.
A toolkit of systematic reasoning. Duckworth has shown us that multiplication isn't a random list of facts handed down from on high.
It is a predictable, navigable system. If you forget a fact, you can logically rebuild it in seconds.
It replaces anxiety with agency. And it really raises an important question as we wrap up this deep dive.
Oh, what's that?
Well, if something is universally accepted as the rote memorization of multiplication tables actually has these hidden, elegant systems underlying it, systems that make learning infinitely more logical. What else is out there?
Hey, that's a great point.
What other hard, tedious facts in our daily lives or in other areas of our education are just waiting for us to find their hidden patterns?
Right. We accept so much of our world as arbitrary data that must simply be endured and memorized.
When there might be a beautiful logic just beneath the surface.
That is such a fantastic thought to leave on. Maybe we are surrounded by logical shortcuts that we just haven't recognized yet, simply because we've been handed too many flashcards and not enough mechanisms. Thank you all for joining us on this deep dive. Keep looking for those hidden patterns in the world around you, and we'll catch you next time.